about the junction field effect transistors, their construction, operation, and their IV, or current voltage characteristics. So previously we have talked about MOSFETs. It turns out that we have other field effect transistors. So we have junction field effect transistors. We have MESFETs, metal semiconductor field effect transistors, which are constructed using employing a Schottky barrier instead of insulated gate. So previously we have talked about applications of MOSFETs. We talked about we took some examples of DC analysis, their applications. Now it turns out that JFETs they were present even before MOSFETs were produced or fabricated commercially. But it turns out the MOSFETs have surpassed the application, and there are certain advantages associated with MOSFETs. So that JFETs are not, the application of JFETs are very limited now these days. So we will keep this discussion on JFETs brief. But anyway, so let's start with the construction. Before construction, this is, let me tell you, this is article 3.6 of Donald A. Niemann, Microelectronics Circuit Analysis and Design, which is your course text. This is the 4th edition. So the content is taken from article 3.6, chapter 3. So to start with, let's start with the JFETs, PN JFETs. So two general categories besides MOSFETs are junction field effect transistors, and they are the PN junction, or you might call them, you might want to call them as PN JFETs, because you will see the construction will be such that you don't have the gate which is insulated from the oxide. So this is like the structure is like PN construction. Okay, so there's the doping regions which are P type, and then this is N type channel. This is an N JFET. Okay, N channel JFET. So, but there is a PN junction, okay, between the gate and the channel. So let's call them the N channel, because the majority carriers in this construction you are going to see that you can see is the electrons. Okay, if it was a P-type JFET, well, these doping regions would have been reversed. So you will have N-type over here at the gate terminals, and then the holes would have flown from source to drain. Okay, so you don't have, for example, if you compare the structure of JFET with the MOSFET, this is an N-channel enhancement mode MOSFET, which means that you want to apply a certain gate to source supply, right? So that you have this, you can create an inversion layer over here. So the conduction starts, and this you can see that this is an N-channel, again N-channel enhancement mode MOSFET. So the majority carriers are the electrons. Okay, so if you apply a positive gate voltage over here, positive term, the gate, this metal accumulates the positive charges, and then this substrate is relatively negatively charged, so most of the holes they accumulate at the bottom of the substrate, leaving the minority carriers up above near the in between the channel and drain and doped regions. Okay, so this space charge induced region will consist of negatively charged or minority carriers in the substrate, p-type substrate, which creates a channel. Okay, then if you apply a VDS, again apply a positive terminal over here, negative terminal over here, this creates a horizontal electric field, and then you have a flow of electron from source to drain. Okay, so but in the construction you see that the gate is there is no gate current. The gate is insulated. Okay, so between the gate and the semiconductor you have the oxide. This is DOX, is the thickness of the oxide. Okay, this is the oxide, or this is the oxide. So this oxide, it insulates the gate. Okay, unless you apply a very large gate voltage, so the electric breakdown of the oxide occurs. Otherwise the gate is insulated. So in all the configuration, common source or source follower, in all these configurations there's no gate current. Okay, so there's no gate current. But if you compare this with the JFET construction, there is no metal gate contact. Okay, and this is a p-type region. Okay, with which there is a gate contact, and this forms a PN junction, just like in a PN diode. Okay, so there's a PN diode on either side of the gate. Okay, And basically what happens is that if you apply the VGS voltage over here and you are going to vary this, you are going to vary the space charge region width. Okay, I mean this, if you want, for example, this is p-type. So if you apply a negative voltage over here, you're going to reverse bias this, and you're going to increase the width such that the channel width is modulated. The channel width is modulated, and if you go on increasing the negative gate voltage, this is positive. But if you apply negative gate voltage, you go on increasing negative gate voltage, the reverse bias junction, reverse bias PN junction depletion region, it increases and it pinches off the channel. Okay, the resistance is increasing. So the idea is that this gate source voltage is again creating the electric field, vertical electric field, that is modulating the flow of electrons. So that's the idea. So that's the difference between the MOSFET and JFET construction. And then there is another type, which is beside JFET. You have a metal semiconductor field effect transistor. So we're going to talk about this a little while later. That the difference between MESFET and MOSFET and JFET is that it employs and it is fabricated with a Schottky barrier junction. What is a Schottky barrier junction? You see, this is a MESFET cross section. Okay, so we'll talk about the details later, but a Schottky junction is that you have a metal gate, okay, and this metal gate again is not having oxide beneath it. It is directly fabricated over a substrate, okay, or a semiconductor substrate. And this is a metal and a substrate. This is a Schottky barrier or a Schottky from the Schottky diode, okay. But the advantages of these MESFETs or MOSFETs is that they're still being used in many microwave applications. They have very small switching times, small transit times. They're used for very fast applications. Frequencies might go up to 45 gigahertz. Okay, so they were very large applications in microwave and radar applications, communication purposes. So MESFETs have still are still in being used largely today. Okay, so as compared to JFETs, so the current the current in a JFET is through the semiconductor region. It is known as a channel with ohmic contacts at each end. Now, if you look at this construction, you have the ohmic contact. So again, you have this gate, source, and drain, just like in MOSFET. Okay, you have three terminals: source, drain, and gate. Since the substrate is usually grounded with the source, you don't need to show in the circuit symbols either the substrate terminal. Okay, so it is grounded, so you don't need to worry about the substrate or the body of the JFET either. The source and you can say that oh, the source and the body of the transistor are short circuited. They are grounded. Okay, so over here you can see the flow of electron is due to the application of VDS, and this VDS is responsible for the flow of the drain current ID, and the electrons, which are the majority carriers in this n-channel region, they're flowing through the semiconductor. Okay, and you have these metal contacts at source and the drain, and due to the electric field, so you see this is positive and this is negative. There is a drain current in this direction, and the flow of electron is in the opposite direction to that of conventional current. So these electrons are flowing in the channel which is sandwiched between the gate p-type regions, okay, for NJFET. So the flow of electron is through the channel. This is the channel. This is the N channel. This is the N channel. Okay, this is the N channel through which the electrons are flowing. But again, you can the resistance of this channel can be controlled by the field effect. That is, if you apply the gate source voltage such that it reverse biases this PN junction, which is being formed from this P-type doped regions with the N-type substrate, if the reverse biasing increases this PN regions so much so that these the reverse biasing is just is choking the channel, then there is no current. Okay, we call this, you'll see that there's a term associated with a very famous term called pinch off voltage. So you've pinched off the channel, so there is no current even with the increasing VDS. Okay, now you see the basic transistor action is the modulation of the channel conductance by an electric field. And this electric field is perpendicular to the channel. So what it means is, again, if you look at the construction over here, even in MOSFETs, the field that you apply at the gate, that's perpendicular to the channel, right? This positive and this negative, this is perpendicular to the channel. The field is perpendicular to the channel in which the electrons are flowing. For example, electrons are flowing in this direction. Okay, so this field is perpendicular. And if you're going to modulate this field, you're going to modulate the flow of electrons. Of course, it depends on the flow of electrons is dependent on the resistance of the channel, which is being controlled by the field VGS. Okay, so since the modulating electric field is induced in the space charge region of reverse bias PN junction or Schottky barrier junction in MESFETs, the field is a function of the gate voltage. So it's always like this in the transistor action. You see the flow of electrons is being controlled by another field or another voltage. Okay, so that's the typical characteristic of transistor. So modulation of the channel conductance by gate voltage modulates the channel current. So JFETs were developed before MOSFETs, but the applications and uses of MOSFETs have far surpassed those of JFETs. So one reason is that the voltage applied to the gate and the drain of MOSFET are of the same polarity, both positive and both negative, or both negative. But whereas the voltage applied to the gate and drain of most JFETs in applications have opposite polarities. Okay, this is one of the reasons. But in today's application, most of the chipsets or embedded systems, microprocessors, cellular phones, you'll find more applications of MOSFETs as compared to JFETs. Okay, so so we have talked about this construction. This is a cross-section of a symmetrical PN JFET. Okay, I mean, you can also call this as a JFET only. You don't need to refer to PN because the construction is as such. You don't have a insulated gate. Okay, the gate is you simply have a terminal sticking out of the p-doped region, which is in the substrate. Okay, and the substrate consists of the majority carriers, which is the electrons. So this is an JFET. The channel will consist of electrons. Okay, and this flow of electrons is due to this supply VDS. Okay, this supply is as such that this, if you look at this positive and negative at the gate and source terminal, the field is as such that this is the establishment of the direction of the field, but the flow of electrons is from source to drain, which is the other way around compared to the conventional direction of the current flow. Okay, so VDS is responsible for the flow of current from source to drain. You can say that, and the channel width is being controlled by VGS. That's the basic construction. So in the N-channel region, channel between the 2P regions, channel which exists between the 2P gate regions, the majority carriers electron flow from the source to drain terminals as JFET is called the majority carrier device. Now the two gate terminals shown in figure 54, and this is 54, are connected to form a single gate. So you can see that this basically both the p-type doped regions are gates, and they are short circuited. The terminals are short circuited, and they're short circuited. Then you are applying a positive VGS. Okay, and in this configuration, the p-n junction is forward biased, so you're not reverse biasing the p-n junction. Okay, so you're not you're not reducing the width of the channel. Okay, or you're not increasing the channel resistance over here. Okay, now this is N channel. Okay, you can have a P channel MOSFET as well. What happens in P channel is, if you can figure this out, you'll have N doped regions at the gate. Okay, for a PMOS, you will have this N over here. You will have N doped region of the gate, and you will have a P type substrate. And the holes are going to flow. Instead of electrons, you will have holes. So the holes are going to flow from the source to drain, right? Again, the polarity of the all the polarities VGS and the VDS is going to change. The direction of current is going to change. So that otherwise the construction is quite similar. So in P channel JFET, the P and N regions are reversed from those of the N channel device, and the holes now flow in the channel from source to drain. The current direction and the voltage polarities in the P channel JFET are reversed from those of N channel device. Like instead of VGS, you will have VSG. VDS, it will be VSD. Okay, the source is going to be at the higher potential as compared to the drain and as compared to the gate. Okay, so also the P channel JFET is generally a lower frequency device, and why is that? Because the hole mobility is a little less than the electron mobility. All right, now This figure 55 shows the basic current voltage relationships, and which is dependent on the gate to channel space charge regions, or you can say the VGS voltage. For example, over here, there's no gate source voltage. Okay, VGS is 0. Then, if you supply a small VDS, there's going to be a current because of the electric field that is established from drain between drain and source region. So this field is not perpendicular. This is in parallel to the direction of the flow of charges. So the electrons are going to flow because of the application of VDS over here. So electrons are going to flow in this channel, right? From source to drain, there will be a flow of channel. And you can see the direction of this current is reversed to the flow of those electrons. So VDS is responsible, small VDS at 0 VGS is responsible for the flow of electrons. What happens when you have a negative VGS? For example, if you have VGS, this is the same VGS because VGS is connected like this, okay? It's short circuited, and then you are going to apply, for example, a negative uh, negative voltage, okay, which is minus V1, let's say, minus V1. What happens is that the space charge region, the width or the space charge region changes, okay. The width of the space charge region changes, which in fact reduces the width of the channel, thereby increasing the resistance to the flow of electrons. So even with increasing VDS, you see as you increase VDS when there was no VGS, the current proportionally increases, and this is quite an ohmic. This was a linear ohmic region being defined by such characteristics. But what happens when you have a negative voltage is that it increases the resistance of the channel. Okay, when you increase the resistance of the channel, you decrease the slope. So that is for the given VDS. For the given VDS, the current ID that you're going to realize is much less. Okay, for example, ID 2 as compared to ID 1. This is VGS 0, and this is for VGS equal to minus V1. So ID 1 is less than ID 0, right? Because you have increased the resistance of the channel. The channel width has been reduced. So the flow of electron is reduced, is compromised, and therefore the current is reduced. Okay. But as you go on increasing VGS to a very large value, let's say V2, which is V2 is much less, is still less than minus V1. Okay, so it's negative. What happens is that there's a state called pinch off voltage that has been reached. So this perpendicular electric field is so large that it pinches off the channel, thereby making the current ID equal to 0. There is no current because there is no channel left for the electron to flow. The channel is gone. So that means that your transistor has been turned off over here. So in this stage, there is no conduction of current. ID is 0. You can see that for V2, ID is 0 over here. This is ID 0. So part A shows the 0 gate voltage over here. Then there's a small reverse bias gate voltage in part B, okay, minus V1. And then if you are still going to apply still a more negative gate voltage, the gate voltage achieves a pinch off. What is pinch off? Pinch off means the channel has been pinched off. The channel width has been reduced to 0, and there is no channel left. Okay, you have reverse biased the PN junction so much. This is PN junction. This is PN junction diode on either side. So the reverse biasing is large, so that there's no channel left. So there won't be any current. ID is 0. So this is the description. So let's go over it quickly. So figure 55A shows an N-channel JFET with 0 volt applied at the gate. The source is a gate ground potential. Small positive drain voltage is applied. The drain current is produced. Okay, so that's the explanation of figure 5A, as I said earlier. With VDS, you have the current. Okay, and since the N-channel acts essentially as a resistance, ID versus VDS characteristic for small values of VDS is approximately linear. So you have a linear, just like a device which obeys Ohm's law. Like you have the gradient, inverse of the gradient is the channel resistance, and which is constant. Okay, for small VDS, as you go on increasing VDS, the current is going to increase because of the horizontal electric field. But if the voltage is applied to the gate of a PN JFET, the channel conductance changes. Okay, so if, for example, if a negative gate voltage is applied, for n-channel JFET, then you're going to reverse bias the PN junction. So the gate to channel PN junction becomes reverse biased. So you can see over here, this is the reverse biasing has started. This region, the channel width is being reduced in part B. Space charge region widens, the channel region narrows, the resistance of the N channel increases, the slope of ID VDS curve for small VDS decreases. So these effects, this is shown in 55B over here, right? This 55B. So you can see over here, the channel has been narrowed down. If a larger negative gate voltage is applied, the condition in 55C can be achieved. This is 55C, and then there is no channel left. So your ID is 0 over here. So this is 55C. And this is what is called the pinch off gate voltage. The reverse bias gate to channel space region completely fills the channel region. This condition is pinch off since the depletion region isolates the source and the drain terminals. So the drain current at pinch off is essentially 0. So that's how you see by applying an external field from the gate to source at the gate, you see you can control the flow of the current. So basically VGS is controlling the flow of the current. Okay. This electric field is because it is changing the resistance or the width of the channel, it controls the current from source to drain. So the ID versus VDS curves are shown in 55C. The current in the channel is controlled by the gate voltage. The control of the current in one part of the device by voltage in another part of the device is the basic transistor action. The PN junction, PN JFET is normally on under depletion mode device. That is, the voltage must be applied to the gate terminal turn of the device. So if you have for example, a depletion mode device, for example, like this, where the channel already exists without VGS, you need to apply a certain VGS, okay, which is negative in this case for N channel and JFET. So if you're going to increase the negative voltage so much that it pinches off the channel, then you're left with no current. The device is off. Okay. In depletion mode, the channel already exists. So in this case, this is on with a very small VDS. Okay. So that's the case. So let's consider another situation in which the gate voltage is 0 and the drain current changes as shown in 56A. So in figure 56A, what happens is for small VDS, ID increases linearly, which is expected. Now we have VGS set to 0 in all three figures, A, B, C of figure 56. So the gate to channel space charge region and the current voltage characteristics for 0 gate voltage are shown. In figure A, you have a small drain voltage. So with a small small drain to source supply, which in turn establishes the electric field, will therefore induce the flow of charges from source to drain, which is shown over here. What happens if you go on increasing VDS for VGS equal to 0? Well, what happens is that since you are applying a positive at that terminal, you are applying more positive voltage. So this is an N-type substrate. Remember, this is an N-JFET. Okay, this is P type doped region. What happens is that you reverse bias this region. So there's more reverse biasing over here. So the channel still exists, but the resistance becomes space dependent. Okay. So what happens is that the channel tapers off, okay, at the drain side, and then increasing VDS is going to produce a slope like this, which means the resistance is increasing. Okay, you're changing the channel resistance. The channel resistance is now the position dependent. For example, over here, the channel is not much closed over here as compared at the drain side, because we have reversed biased it more over here. This is positive. Okay, this is positive. This is negative. So as more positive charge is accumulated over here due to large VDS, you have more reverse biasing at the drain side. Okay, so this increases the resistance at the drain. Then as a result of that, the device as a result, increasing VDS does not help in increasing the current ID because of the high resistance at the drain terminal. So as you go on increasing VDS, as more and more charge is accumulating on the drain terminal, what's happening is that a point comes, then the channel is still like this, it's still tapered off, but it closes at the drain side. At the drain side, this since this is N-type region, and this is positive. So at this region, you have reverse biased the drain side so much that the channel closes at the drain. So this is the point where we call this saturation, because beyond this point, increasing VDS does not affect ID anymore. Although this is for a certain VGS which is taken 0 over here. Okay, this VGS is 0. Although applying a certain VGS, a negative, might still reduce ID, or in case you apply positive, it might increase ID in other case, the other way around. So VGS is still going to affect your ID, but increasing VDS beyond VDS saturation does not increase the current. The current stays almost constant. Okay. So you see in part B there is a large drain voltage. In part C the drain voltage achieves a pinch off at the drain terminal. So it's not the channel that has been pinched off completely, but the drain has been pinched off when the VDS has increased very to a large value. So as the drain voltage, it says over here, as the drain voltage increases, it becomes more positive. The gate to channel PN junction becomes reverse biased near the drain terminal, and the space charge region widens, extending farther into the channel. Okay, so the channel basically acts essentially as a resistor, and the effective channel resistance increases as the space charge region widens. Therefore, the slope of ID versus VDS characteristic decreases, as shown in figure 56b. So you see over here, as you're going to increase VD, you're reverse biasing this. You're reverse biasing the drain terminal. Okay, so because of this, the resistance is increasing at the drain. So you see there's a change in channel resistance, so the current is decreasing. Okay, so a point comes beyond where the transistor becomes saturated. We say the transistor is saturated. So after this point, ID is independent of VDS. You go on increasing VDS, doesn't matter. Okay, because the channel has been pinched off at the drain terminal. Okay, so the effective channel resistance now varies along the channel length. Since the channel current must be constant, the voltage drop across the channel becomes dependent on the position. You see over here, the channel resistance is position dependent. For example, there's not much resistance over here for the flow of electrons, but over here the resistance is very high for the flow of electrons. So it's independent of VDS right now. Now, if the drain voltage increases further, the condition of 56C is produced as a result. The channel is pinched off at the drain terminal. Any further increase in the drain voltage will not increase the drain current. The ID/VDS characteristics for this condition are shown in the figure. So the drain voltage at the pinch of VDS sat is produced. If VDS is greater than VDS sat, the transistor is biased in the saturation region. And the drain current for this ideal case is independent of VDS. This is what we have seen over here. Okay, so if VDS is greater than, if the transistor is biased as such that VDS is greater than VDS sat, then the transistor is in the saturation region, and the drain current of the JFET is independent of VDS. Okay, so the drain current is independent of VDS. So this is saturation region. This is the ohmic region or the linear region, and this is the cutoff region. Okay, that's all.